So I'm just going to talk about alkenes and alkynes. I'm going to go through all the drawing types on these two slides. So we've seen structural formulas in the previous lesson. We saw condensed structures, but we haven't seen the last type. So alkenes is the second family. That's a term you need to be familiar with. You may get a question that says, here's a drawing, what family does it belong to? Alkenes are organic compounds that contain only carbon and hydrogen, so they are hydrocarbons. Okay? They are not hydrocarbon derivatives. Okay? To be a member of the ene family, you must have at least one double bond. We focused in high school on naming one double bond, but you could have two or three. You'd see the same prefixes. If you had two double bonds, you'd see di, telling the reader there's two. If you had three double bonds, it'd be tri. Okay? But that's not largely where we're going. Okay? When you put in a double bond, okay, something has to be lost. Carbon can only have 4 bonds. So to add a double in, you're going to lose some hydrogen to make room for it. And that gives rise to a term called unsaturated. Okay? And this is with respect to hydrogen. Okay? The alkanes that we saw earlier are saturated or filled with hydrogen. When you put a double bond in, you have unsaturated or unfilled it. Okay? The double bond removes 2 hydrogens, one on each side of the carbon that has the double. If you've ever heard of unsaturated fats, that's where this comes from. An unsaturated fat has a double or triple bond, and it affects the boiling point and melting point of those fats. Okay. So here's a little bit condensed structure. Okay. That is not a structural diagram because the H's aren't all dashed out showing their bonds. Okay. I want to name this. I have to find the longest chain that includes the double bond. Well, there's no branches. There's just one continuous connection of carbons. So no worries about keeping the double bond in the longest chain. I'm going to have to count where that double bond is. And visually, it's going to be closer to get to on the right. I don't have to count both ways and figure it out. What carbon-carbon bond is the double? Well, it's not the first one, it's the second one. So that's all the information we're going to need to name this. There's 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's oct. There's a double bond. So we're going to put ene, and then I put dashes and a blank to put the number of the location of the double, which we've already figured out is in the 2 positions. So this is octuene. In my rules, rule number 3 is, do we need a number? Okay. We need a number whenever there's more than one possibility. Okay. Is there oct something enes that have other numbers? And absolutely. You could have the double bond in the 1 position. You could have it in the 3 position. You could even have it in the 4 position. There are 4 possible octuenes, so we need the number to tell the reader which of the 4 it is. Now there's only 4. If the double bond was way over there, that would be 1 from the end. That would be an oct-1-ene. So this is our name with that number included. I'm going to do a fully condensed structure. I'm going to leave out the word structure to try to keep my board a little cleaner. And then I'll do a line structure, but I'll just write the word line. So condensed structures have no lines whatsoever. All of the bonds have been removed. So at the very beginning, we have C with 3 H's. Then we have a C with 2. That's familiar. That's what we saw with our anes previously. C with 2 H's. We're kind of in the middle-ish. C with two H's. C with two H's. Then we get to a C with just one H. And then next to it is another C with just one H. When you start seeing this kind of lack of hydrogen in the middle, you got to be thinking, is there a branch or is there a double or triple bond there? The very end of this molecule has a CH3. Okay. There are 8 carbons there, so it looks good. This is correct. So that's a condensed structure. With the double bond, a little harder to pick out, but that double bond would be where I've double underlined it in red. Okay. The red isn't part of the answer. It's just me connecting where that double bond is hidden. Okay. Okay. Chemists need short forms. Instead of drawing out big, complicated structures, we could condense it, which only shows the atoms, or we could do line structures, which is the total opposite. All the letters go, and the carbon-carbon bonds stay. The only thing in condensed structures are the carbon-carbon bonds. So if we keep the bonds and get rid of the letters, okay, the letters are gone. The letters are gone. We just have these dashes zigging and zagging. Okay. Now to write the line structures, the guide I tell students is drop the pen and say 1. Where you've dropped the pen is your first carbon. And every time you zig and zag, you count another carbon to get to the count you want. Okay. And you'll notice the zigging and zagging matching the structure at the top. So I'm going to drop and say 1, 2, 3, 4, 5, 6, 7, 8. Lift my pen. Every end of a line segment is a carbon. No, I haven't put the double in yet. But that gets the 8 carbons. That gets the stem or the parent out. Stem parent synonyms. Okay. Where's the double bond? Okay. It's not the first carbon-carbon bond, it's the second. So there's the first carbon-carbon bond. It's not there. It's here. The second carbon-carbon bond is where we have the double. So this is where you double up your line to show the reader there's a double there. That is the line structure for octuene. Or any rotation or mirror image of this. Any flip would be the same molecule. So the black is the answer. Strategies that I teach to have you decode line structures is to work backwards to get the count. If you put a circle at every intersection, the count pops out. So I'm using a different color. This is not the line structure. It's decoding it. There's the end of a line segment. There's a carbon. There's where segments meet. There, 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 there. And that would be the end line segment, the end carbon. If you put the circles in on top of a test question, there's 8 green circles there. And it can help make sure you're not off 1 in the count. So again, the green is just a strategy. I'm going to take that out of the line structure. So that's alkanes. Sorry, alkenes. E-N-E double bond. Okay. Alkynes. The Y is pronounced like an I. This is our third family. Exact same first statement. They're organic compounds that contain carbon and hydrogen only. And there's at least one, and we will focus on one carbon-carbon triple bond. Adding in double and triple bonds make molecules unsaturated. Similar to redox, there's going to be a fair bit of vocabulary to know. This is a bit of a memorize / apply naming rules. It's not a math figure out unit. The second bond requires the removal of two H's. The triple bond requires, or the third bond requires the removal of another pair of H's. So that's why I say two pairs or four H's have been removed from an ane to make an yne. Naming this, find the longest chain with the triple bond. Well, this looks to be continuous. So the only continuous chain has the triple. That's 1, 2, 3, 4, 5. So the stem or parent is pent. I see a triple bond. So it's going to be an yne. And there's several places that triple bond could be. So I'm going to need a number to tell the reader where to find it. I'm going to have to decide which end to count from. I'm going to count from both ends. Don't label both. In your note, I'm going to erase one set. Okay, this is actually going to be the wrong way to do it. If I counted from here, there's the first carbon-carbon bond, there's the second, there's the third. But that's not the shortest end. So calling this pent 3-yne would be incorrect. Okay, would be one of the distractors, the wrong answers on an exam. Okay. So we have that number 3 in our head, but this is the short way. That's the first carbon-carbon bond, that's the second. So that's the correct end that we have to count from. So this is pent 2-yne. This is a unit that it's actually good not to look at the answers. Normally I would say redox, thermo, look at the answers, try to eliminate A, B, C, or D. Here you can get sucked into a wrong distractor if you look at the answers. So I'd almost hide them, just name it yourself and then look for that right answer. So you don't accidentally. You get very biased towards A or B if it looks right. You're like, oh, that's pent 3-yne, it's got a triple bond. Okay, it's got 5 carbons, and then you don't even look that D was the right answer, naming from the correct side. Okay. Let's do a couple more drawings, those ones you saw before, and then you'll practice. So I'll do the condensed structure. So we've got a CH3 at the far left, a CH2, then we get to a carbon that has absolutely no H's attached to it. So that's all I can write for the third from the left carbon. Okay. The next carbon also has no H's attached to it. Okay. When you see that C to C with no H's, that should be screaming double, triple bond, something going on there for you to think about. The very end is the kind of as expected carbon with 3 H's. So there's nothing unusual going on there. Okay. So that is one of the correct structures. Okay. Or any rotation of this would be correct. Okay. Molecules, we tend to write them left to right because it fits nice on paper. But on an exam, okay, the answer could be flipped or vertical. So, you know, it could be sort of flipped. Now, I'd flip the H's around, but you could have the double C's with no H's on the left, or you could have them written on the right. It's still the same molecule. It's not different, okay? It could be up and down. That's the same molecule, okay? Or it could be up and down this way, okay? So that's one thing that'll start doing some more, is getting you used to, you know, any rotation of it is the same thing. And when you're working on a workbook, you can literally sometimes take your workbook and literally flip it and compare it to a friend and see if you actually did the exact same structure just with a rotation. Okay. Okay. Line structure. So we've got 5 carbons, a double bond on the second one. Okay. I'm going to do the 2 line structure so it would be correct. 1, 2, 3, 4, 5, lift. Our bonds, I'll put in a different color because they're not part of the answer. 1, 2, 3, 4. Now that count helps guide you to put the triple bond in on the second one. So that is correct. It kind of mirrors or matches the drawing I did. Okay. But a student would be equally correct if they just flip the right for the left. As long as the double bond is 2 from an end, it's correct. So I could go 1, 2, 3, 4, 5. Okay. And I could count the other way. Okay. It's just the mirror image. It's the same molecule. So I just rotated it around 180. I'm still the same person this way when I rotate. Okay? I might look different, things are rotated, but it's the same molecule, you're the same person. Okay? And that can get a little bit, that can take some time to get used to, 2 drawings that are flips of each other and realizing that they are the same. So now it's time to do some practice. So I've got some problems for you to work on. I'll recap some of these. Okay, I've left lots of room for D because I'll put the answer up for D. That's about as hard as you're going to see on an exam to deal with. Now we've got some missing numbers in B and C. So those should have numbers, but they were dropped. So you have to think of what's the missing number there so you know how to draw it. Okay. So the answer to A. So I gave you a list of steps, and we have to decode these in the same order. So way back in those steps that we got many slides ago, okay, the first thing we deal with is the parent or the stem. So that's the first thing we're going to decode. Then the second thing would be the ending. And then the third thing I want to decode is the front, the alkyl groups. Okay. So that's the sequence I'm going to go through. Okay. So we have hex, which means 6 carbons. You can zig and zag them or ignore Vesper and just put them in a straight line. It's probably easiest to put them in a straight line, but if you want to zig and zag them, that's a bit more thorough, but not what you're tested on. So I have 2, 4, 6. Okay, so I've covered the hex. I put 1 dash between all of them. I don't have to add anything else because it's an ane. It only has single bonds. Okay. Now I'm on to my red number 3, which is the side group. The second carbon has a methyl. Okay. Now we're going to get 2 answers. You could start numbering from the left or the right, and they're both correct. They're both the same structure. Okay. I'm going to pick the left for my numbering. Okay. If there were several pieces, we would have to stay from the left. So if there was a methyl and an ethyl, we can't switch sides halfway. And as we build up and add pieces, we have to stay on the same side. So the second carbon over has a methyl, which is 1 carbon. I could go up or down, it doesn't matter, as long as the second carbon has another carbon coming off of it. Okay. So that's all the carbons. Then we had that bonding capacity slide reminder from Chem 20. Every carbon has to have 4 bonds. So I'm going to add in all my H's in this hydrocarbon to get to 4 bonds. So this first carbon is missing 3 bonds. It now has 4. This top carbon needs 3 more bonds. This second carbon has 1, 2, 3. It only needs 1 more. Now we have a whole bunch of carbons with 2 bonds and needs 2 H's. Then we get to the very end, and our carbon needs 3 bonds. So that's one of a few correct structural diagrams. Okay? The mirror image of this would be also correct. So let's see, continue to work on B and C, and then kind of everything thrown at you in D. Okay. So I'll recap B and C and then pause a little bit before D. There's lots to talk about these. They are tricky, but you're not going to learn by watching me do all these examples. You need to try, maybe fail, learn from that. Failing is an important part of learning. You could just not practice and never fail, and you would never learn. You're going to practice and fail a lot in organic, but once you get about a third of the way in, the failing starts to go away, and hopefully by the end, it disappears if you practice. So a tricky one. There's no number here. We've got a propane. You know, start with the prop, then the ane, then the dimethyl. Okay? A lot of this is getting you to be very rigid in your order. Okay? You're not winging it, stem, ending, prefix. So prop is 3. Ane is all single bonds. So I would hope you could get there quickly, or soon you'll be able to do that quickly. And then you've got the tricky dimethyl piece. Okay? And it's like, where can they go? Okay? Now we're just starting to develop this skill set that you cannot put methyls at the end. If I put a methyl at the end, this is wrong. This is actually one nice continuous chain. It is not a branch. It looks like it's a branch because it's sticking up, but it's not. Our chains can zig and zag. That is a butane, not a methyl propane. So you can't put a methyl group there. Okay? So that's got to go. Okay? For the same reason, you can put a methyl group at the other end. It's butane again. Okay? So it doesn't matter what problem we're dealing with, you can never put an alkyl group, methyl, ethyl, propyl, butyl, on ends. And if you can't put them on the end, the only spot you have is in the middle, the 2 position. Okay? The numbers are 2,2-dimethyl propane. But the 2's were dropped because both of them have to go off the middle carbon. Okay. Now there's a bunch of hydrogens to write in. Now there's a few different drawings you could do. Okay. I put one of the branches up and one of them down. I'm going to put some redundant drawings up. Okay. You could also have gone and put them both up. Okay. There's still that middle carbon has 4 bonds coming off of it. Okay. No drawing is perfect because in real life, that is a tetrahedral structure. Okay. Where things are going in kind of all directions spread out. So there's no way we can draw a tetrahedral structure on a flat piece of paper. You have to do some kind of projection. Okay? So these are just kind of distorting the truth slightly differently. Okay? But the connections are correct. Okay? No, I never put my hydrogens in. I'm just quickly throwing in the dashes. Okay? She should have one of those 2 possible answers. Okay. Propene, also a little bit tricky because there's no number, but it's a little easier than B if you can follow the rule stem first, ending next. Okay. Prop, 1, 2, 3. Ene, there's no number, but the number would have to be the shortest way. Okay. So I could do a drawing from this side, and that would be the 1 position. Or, also equally correct, you could do prop and put the double bond on the other side. Okay. Now I would be numbering from this side. And no matter where I put the double bond, the shortest way to get there is the 1 position. So this is kind of a prop 1 ene with the number dropped because the double bond has to be on an end, which will be in the 1 position, whether you draw the double bond on the right or the left. Prop 2 ene is never a correct answer. Prop 2 ene is not minimizing the number. Okay. Prop 1 ene is. So that's, see, I didn't put my hydrogens in. Okay. That's not a correct drawing, but I'll often do this in my notes for speed. I'll put the dashes and not write the H's in. You have to make sure on tests and quizzes you write those H's in. I'm actually not that concerned while you practice. If you do this type of practicing, just realize it's not technically correct. Okay. Okay, I'm going to put up the answer for D now. Again, realize you could have done this from the right or the left. I'm going to have to pick one. So, structure to deal with this, stem first, ending second, and then we've got a whole bunch of alkyl groups third to read through. So, non is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I just put them in a straight line. I'm not bothering with Vesper, the bond angles. So there's non, 1 ene, double bond in the 1 position. I'm going to count from the left. If you put your double bond on the far right, you're correct. You would have to have the mirror image of mine. Now I've got 3 different alkyl groups to deal with. I have 2 ethyls. Ethyl means 2 long branch. It's not 2 branches, it's 2 carbons in the branch. So my first, my second, my third carbon needs a branch of 2. I could go up or down. I'll go down, I got more room. And on a test or quiz, go wherever you have more room and it's a clearer answer. Down 1, down 2. Okay. Now all of these carbons are going to need to have 4 bonds. I didn't put the H's in, but I put dashes, and there'll be an H on the end of each of those dashes. So that's the 3-ethyl. Okay. There's a 4-ethyl, so that's my 4th carbon. Again, I could have went up or down. They both don't have to go the same way. Last, I have a 2-methyl, 1 number, no prefix, just one of them. Here's my second carbon, and I'll keep going down, but I could have went up. Meth is 1 carbon. So that's everything dealt with, and then I'd have to put hydrogens all over the place to get 4 bonds. So that my front carbon would need 2. My second carbon has 4 bonds. My third carbon has 3. My 4th carbon has 3. My 5th needs 2, needs 2, needs 2, needs 2, needs 3. And I'm not going to write all those H's in. It's boring for you to watch me write them in. So it's long, but over time and practice, you'll see long is just more simple steps where Right now it might seem confusing, but you're just, if you can add 2 numbers, you can add 7 numbers. Okay? And that's kind of what we're doing. We're learning all these pieces, and you might have to put a whole bunch of pieces together, but you just do it one at a time. So that is our first 3 families summarized.